Hey everybody, welcome back. Mr. Smith here. In today's deck, what we're going to do is talk about some basic theory and math behind the idea of electric currents, concepts that you may have heard of in middle school, you may have worked on in Physics 1, and which may be no big deal for you. So we'll start with the theory part, and I think you might learn something here anyway. When we talked about the idea of static electricity literally means charges not moving. So we talked about piling up a large number of coulombs or a lot of charges of one type in one location. So big piles of charge. In current electricity, instead we talk about those charges moving in a constant basis. So rather than in one big catastrophic spark like happens in our Van de Graaff demos, we've got a steady stream, kind of like a river flowing or like water moving through a garden hose. The idea of voltage also is talked about differently. In static electricity, we talked about voltage as being a measurement of how unnatural the charge distribution was. And in current electricity, we talk about voltage as being the push behind the charges. Really, in both cases, they're really related to electric field. But the way we talk about them and think about them in our heads maybe is a little different. If you'll remember, Benjamin Franklin in the 1750s was doing his lightning experiments. And as we talked about, the Founding Fathers and everybody who could get their hands on a Leyden jar played with them, and they figured out that muscles were electrical. So many scientists played with this experiment, but the credit goes to Luigi Galvani for experimenting ad infinitum with countless frogs, doing awful mean stuff to them that I'll tell you all about here. Here is a graphic where you can see that Galvani has taken apart a frog, preserving its spinal cord and its leg muscles. And what did he do? He found out that if you touched the spinal cord and the leg muscles of this frog with a probe made of two dissimilar metals, you would activate the frog's legs. And you would do it over and over and over, almost infinitely. You would do this until the frog's legs got dried out. So if you kept them wet, you could go on for a long time. Poor frog. So what was the discovery that he thought he'd made? He believed that electricity was a thing that resided inside of all living objects. We know that he was wrong. Here's how we know he was wrong. About 20 years later, another Italian researcher, Alessandro Volta, discovered that you could throw away the frog's legs, that all of that was needlessly cruel and served no point anyway. What he did was to make a sandwich out of different types of metal. So you see on the very top, we've got several buckets of salt water or acid or something like that. And what we're doing is we're stringing wires between them attached to little bits of metal. This picture is a little easier to follow. What he's done is to make a sandwich out of, let's say, copper and zinc and copper and zinc and copper and zinc. And when you do the same thing over and over and over and over, they thought of cannons. And they called them a battery, where one cannon is a cannon and a bunch of cannons is a battery. This is where the word battery comes from. It's a bunch of chemicals layered, separated by fabric that was soaked in either acid or salt water or something else that we call an electrolyte now. What was the frog's leg? The frog's leg was just the moist thing between the conductors, and it was actually irrelevant to the science. When Volta got really good at this, he built this enormous, this is a couple feet tall battery, and this thing could deliver a wallop. This could deliver a spark that you would really feel, that you wouldn't want to get hit by. And it's made of hundreds of these layers of copper and zinc separated by fabric and salt water. So let's go forward with that discovery another 20 years to where the battery becomes a truly serious scientific device. So Humphrey Davy was a student of characters like Antoine Lavoisier, and he was also a teacher to guys like Michael Faraday. So Humphrey Davy's a fascinating character in the history of science. What you can see down here in the bottom part of this graphic is just an amazing thing. If you look at these human beings down here for scale in our example, you can see that these batteries are very, very long. So if you follow the last slide, you get that when a battery has a lot of cells in it, so copper, zinc, copper, zinc, copper, zinc, or lead, copper, lead, zinc, something like that. When you had a big sandwich, you get more voltage. You would get a bigger spark in a bigger, more powerful battery. There's another side of it too, though. The size of the cell, the physical size of the metal plates you use, had a lot to do with the size of the spark, the thickness of the spark. So in other words, the number of charges that would flow. So it sounds like what we're getting here is similar to what we talked about with Van de Graaff, that the power that gets delivered by a Van de Graaff has to do with how many charges flow and also the voltage that each charge is flowing through. Anyway, what Davy did with this battery is, in public demonstrations and in his private research, he was the first human being to ever lay eyes on the element potassium. He was the first person to ever take baking soda and rip it apart chemically. And in turn, he separated the chemicals barium, magnesium, calcium, strontium. Other scientists did the same tactic and separated aluminum and all of the other elements that are on the left-hand side of the periodic table. Why is that so amazing? No one had ever seen these chemical elements. And probably in the history of Earth, these chemical elements had never been seen since the invention of oxygen by anaerobic bacteria billions of years before Davy laid eyes on them. So these chemical elements were locked away inside of chemical compounds that couldn't be broken by ordinary fire. Why? Ordinary fire is not hot enough. What Davy had done is to grab a battery with enough power to rip apart chemical compounds that were untouchable by any other means. So absolutely amazing and fascinating. So how does it all work? Well, check it out. The battery works because of a thing we call electronegative difference. So if I zoom in here on copper and I zoom in on zinc, you'll see that they occupy different places on this table of electronegativity. Well, electronegativity simply is how hard an element wants to hang onto its electrons. So if I make a sandwich out of these guys, it would appear that copper wants to hold on to its electrons a little harder than zinc does. Righto. So if you've ever made one of these things, a lemon battery, you can take a copper, this guy right here, a penny, jab it into the lemon, and take a piece of zinc and jab it into the lemon. And what happens is, because copper wants the electrons a little more than the zinc does, the electrons flow in this direction. What does that mean? Well, I've got an electric field on the inside that's been established like this. And those charges will flow until I've changed chemically these metals right here. One of them gets oxidized, this guy. One of them gets reduced. And when they're finally chemically satisfied, the reaction stops. But this can go on for a long time, so hence electrical currents. All right. Now, where do we go with this? Well, let's show you some the big table of formulas. It's really just going to take the formulas we've used in static electricity and adapt them. So if charge is Q, current is how much charge flows for time. If work is QV, then power is work divided by time, or current times voltage. So if you notice what I did, just took this guy right here and popped him in here instead of work equals QV. We just adapt this formula, power equals IV. And finally, you may have seen Ohm's law, which says that the current that flows in a steady state situation has to do with voltage, how hard you push, divided by resistance, how much the material fights your ability to push charges through it. Okay, a few examples real quick. Here's an oldie and a goodie, something like this. If I have a voltage of 120 volts passing in 10 amps of current, they're asking us how many electrons pass through the machine's motor. So our 10 amps, we know, is really 10 coulombs per second. And I know from before that an electron is 1.6 times 10 to the negative 19 of a coulomb. That's one electron. And I can just do the math on that, and I get a horrific number of electrons passing through the motor, 6.25 times 10 to the 19 electrons in my ordinary vacuum cleaner. Okay, there you go. Moving on. Here's an Ohm's law question. Well, if I equals V over R, then it stands to reason that R equals V over I. And I'm just going to go ahead and plug in. Got 120 volts, current of 10 amps, and this looks like a 12 ohm device. Okay, moving on. So a voltage of 120 volts, 10 amps. What's the power in watts of this device? So the way that works is just P equals I times V. So current of 10 amps, so 10 coulombs of electrons every second, passing through 120 volts, and we get 1200 watts of power. And then finally, let's think about how we pay for those things. Kilowatt hour was invented, and you'll see why, by people that had to pay for electricity. So how much energy is this in joules if I run this vacuum for 10 minutes time? So remember how power equals work over time? Well, that gives me that work equals power times time. So if I go ahead and take my 1200 watts and I multiply it by, I'll cheat for one step here and write 600 seconds, I get a pretty hefty number of joules. Oh, well, here's the deal. You use way more electricity than that in a month in your house. And so because people don't want to pay for billions of something, the kilowatt hour was invented. So you should check your electrical bill at home and see how this works. A kilowatt hour is two things. It's either 3.6 times 10 to the 6 joules. So 3.6 times 10 to the 6 joules. So I could just convert this to kilowatt hours by using this conversion factor. And what it is literally 1,000 watts of power operating for 1 hour. So what I can do is I can reorganize that formula that I worked with before and just rewrite my 1,200 watts as 1.2 kilowatts. And then if I had wanted to, I could write this 10 minutes or 600 seconds as 1/6 of an hour. And if you notice, what I've got now is kilowatts times hours. So that's what this would be. So if I just multiply those two numbers, I get 0.2 kilowatt hours. And there you go. All right. This one right here, if you do it by the conversion factor, will work the same exact way. Check me if you want to. Finally, my favorite device of the last 10 years probably is this one right here, the Philips Hue. It produces the light of a 60-watt light bulb of the old variety, and yet it draws 5.4 watts. So pretty cool. Has saved a lot of electrical energy and a lot of climate change gases from having to be made. So how much current does it draw? Well, we're going to take P equals IV and solve that thing for current. So I equals P over V. And if this guy draws 5.4 watts and at 120 volts, then what I figure is this thing draws 0.045 of an amp. So a super small amount of electrical current. And if they want to know what the resistance of this is, it's going to be a lot. So resistance equals V over I, and 120 volts divided by my 0.045 amps is going to give us 2667 of the ohms that we talked about of resistance. Okay, so that's it with the basics. So bring your questions to class. Let's talk further and take care. Thanks for watching. Bye-bye.